11. We can start slowly. Anyway, I want to spend a minute or two just with a recap of what we did last time. So we did two lemmas. We did the diameter bound, and we will be using it, or more precisely, we'll be using the proof that we did of it more than the actual statement of the lemma. And we did this nice lemma about finding cycles or paths in weak expanders, and we started kind of introducing the whole machinery and various definitions of both weak expanders and strong expanders. And at the very end, I wrote this definition on the board and gave you an exercise to think about how fast these things expand. So let me now slowly go through it, because it's going to be the main thing we're going to be playing with for the rest of the course. So we say that an n-vertex graph G is a sublinear expander if, whenever you take a subset of its vertices, and don't worry for the moment about what is written here, I'll come back to it in a moment, what you get is this epsilon over 4 factor expansion going out of U. Now, the key distinction here is that this epsilon, unlike before, is not an absolute constant. It's something that depends on the size of the set. Okay? And how does it depend on the size of the set? This equation tells you how it depends on the size of the set. Right? So if your set U has size n to the 1 minus epsilon, you should get an epsilon factor expansion. Okay? So technically, for convenience, I would like to put here an upper bound. So smaller sets always expand better. So this is something that we'll get for free, and it will make some things in the proof a bit more easy. I'll not need to kind of work with precise sizes of U, but if I get an upper bound, then I can expand it by whatever that upper bound tells me I can expand it. And this is the reason why epsilon is kind of given at before. But really, forget about all this and think about it with equality. This is how epsilon is defined. It also tells you why, if you uncover what epsilon is here, you'll get some logs, you'll get something nasty, and it's kind of much less clear what's actually going on. So stating it this way and backwards, this might look a bit unnatural, but it actually makes things nicer. So also, just to understand what's happening, if epsilon is an absolute constant, that means if your size of the set is n to the 1 minus epsilon for an arbitrary small constant epsilon, you expand by a constant factor. If epsilon is 1 over log n, that's more or less the smallest that you ever actually want to take it, then this becomes n over 2, and I really want every set up to size n over 2 to expand by roughly 1 over log n factor at least. Okay, so these are the two kind of extremes how to think about the strength of expansion here. Great, so let me now tweak this definition a tiny bit extra, because it gives you a crucial extra bit of power for lots of different problems. And this is what's usually called a robust sublinear expander. And the only thing that gets added is that you're also allowed to forbid a bunch of edges. So for every f, which is a forbidden set of edges of G, which size is bounded by epsilon average degree of G over 4 times the size of U, you get this same expansion in G minus f. Let me draw a picture. So previously we had our G. It had this kind of scale of different scales of expansion depending on how big it is. You got some number of vertices so it was epsilon times size of U that you could reach. So what I'm saying now is actually I want to be able to forbid a bunch of edges. And you get to choose these edges after you picked your U, right? So their size is also upper bounded by the size of U times epsilon times D. We'll get back to the quantitative thing. And I still want to get essentially the same expansion. Well, the same as because I wrote it that way. But you could get it with a 2 if you didn't care about the edges instead of 4. OK, so we'll see in various examples why this gives you a bit of extra power. Actually, for the first one we'll do, well, because we're doing a weaker problem, it does not. But just to explain what's happening with the parameters here, again, if you think of epsilon as an absolute constant, then I'm allowing you to forbid essentially a constant proportion of edges touching U, and I still get this expansion. Right? The D of G is the average degree in the graph, so generally you will not expect around U to get more or less, that's now a bit iffy, but more or less than average degree of D, many edges touching it. And I can forbid that many and still expand. And I can also forbid them here, which will then kind of tell me I have somewhere else expansion. And really, just to draw a picture which is trying to explain what's going on here, maybe let me first finish the quantitative. If epsilon is 1 over log n, then you can forbid up to 1 over log n fraction of the edges, and you still get this vertex expansion. Also, if you like to think about it in a bit of two different ways, if you forget about the vertex expansion, then this just tells you have this much edge expansion. Right? So if I don't really care how many new vertices I get, just how many edges I have, if I have less than this many edges touching U, I can delete them all, and I would contradict that. I would not have any new vertex. I deleted all of its edges. Right? So if I don't care about this, then this is just talking about edge expansion. Yes? Mm-hmm. Average degree of G. So this I'll be using a lot. Thank you. Okay? So just, it will be happening a lot, and I did not put it. Thank you. Very good. Right, so this definition is really somehow intertwining the vertex and edge expansion into one single thing, which will be useful in various places. So just to draw one example of what I wanted to kind of, well, with this epsilon, maybe it's a bit less clear, but this robust extra condition is allowing you to recover from pictures that look something like that. So if we just compare it to 1 over log n expansion, then very small sets might have just a single edge going out. And then adding this type of F condition now forbids these pictures from happening. So it kind of gives you back this robust connectivity properties that, that I put in the vague definition of expansion at the beginning. But this is more a kind of very hand-wavy intuition that is just trying to explain a little bit why we call this robust and precisely the type of property that it will let us do again. So somehow that even if you delete a bunch of stuff from your picture, you still get this diameter type nice properties bound. Very good. So any questions about the definition? OK. If not, let me prove a lemma, which is kind of the main point why we care about this, which is that you can find one of these things in any graph. So lemma, and I call this path to expander lemma. So in any non-empty graph and vertex graph G, there exists a subgraph H, which is a robust sublinear expander. So that's my abbreviation for this, because it's long to write it. And it will appear such that the average degree of this H is at least the average degree of G times log the number of vertices in H divided by log the number of vertices in G. OK. So let's stare at this lemma for a moment. So I should say that it's actually one of a kind of whole family of expander lemmas, path to expander lemmas that exist. It's a relatively recent one which kind of cleans up of various different things that existed before. It still doesn't really apply for very sparse graphs. So if you think about it, if our d of G here is smaller than log the number of vertices in G, then H being a single vertex is actually a valid, robust sublinear expander subgraph and makes it useless. Okay? So if you want to get a similar lemma for something that works for large constant degree, this was done by Komlós and Szemerédi, and in reality, they even done some version of this. They just left it in a kind of worse state and with somewhat, different notion of robustness and you need to pick your own functions, etc. Let me not go into that. But if you look at the exact lemma that they were using, which works already from constant degree, it becomes much messier and much harder. So as a kind of first course on sublinear expanders, I don't want to go and do that one. I'd rather stick with graphs that have degree at least polylog, and for which this one is going to be kind of nicer and better and let us do various nice things. So that's one side of the story. Also, it's actually even not, in a certain sense, optimal if you have better guarantee on the degree. So you have an exercise, I'll maybe write it after the proof, but in the notes that asks you to prove a better version of this lemma in the sense that you get better expansion than what's written there if you have polynomial guarantee on the degree. So if you have at least n to the alpha minimum degree, then you actually can do better than this. So unfortunately, I don't have one big, nice lemma which unifies all of these pictures. In a sense, you can take this Komlós and Szemerédi one, and you can sort of, with some work, recover all of these things from it. But it's a much, much harder thing to digest and write down than just working with the specific one, which is kind of tailored and in certain sense stronger than what they did for the specific regime that we'll be interested in. So as a sort of introduction to sublinear expanders, I want to stick to this lemma and leave you as an exercise to do because it's the same proof for the bigger one. And also even for the lower degree, it's the same proof that I'm going to show you. So they all follow the same kind of proof pattern. So once you see one, you can do any you want. But depending on the problem you're working with, you need to adjust things a little bit. Very good. But besides this, it's really kind of an amazing lemma, which says that you take an arbitrary graph about which you have no idea anything about it, and suppose you're looking for some structure inside of it. I don't know, a cycle, a subdivision, or a subdivision of a clique, topological clique, whatever you like, any extremal problem you want. What this tells you is that if you're trying to control the answer only by the degree, you can just zoom into an expander of that form and just solve the problem there, right? So if your degree is at least log, then by passing to this lemma, you've lost nothing in terms of the degree, right? If d of g is bigger than log of g, then the degree guarantee we get on h is at least log of h, which was the same sort of thing we had on the g, right? And now instead of finding your structure in an arbitrary graph, you can go and find it in this sublinear, robust sublinear expander. So you're now working with something much stronger and with something which we have lots of tools about and can do various things. And that sort of starts to look like a random graph. So in some sense, if you're familiar with regularity lemma, it works for super dense graphs. And there it tells you that you can find some random looking parts that actually decompose your graph, and then you can start doing lots of useful things. This is something that's designed to do something sort of similar, but at a much lower degree. Say it's starting at log n. It also gives you much less power than regularity lemma, though. There is, if you go to linear degree, actually a whole theory of this sublinear expander stuff, which actually allows you to bypass regularity lemma and give nicer proofs very often. Kuhn and Oss, who's developed lots of this with various co-authors. I'll put some links in the notes, but we will mostly not touch on that, other than one exercise for you. Yes?
Yeah, so in this lemma, do you get any kind of non-trivial bound on the size of it?
No, so you need to extract it from this.
Okay.
That's the kind of thing that why it's, telling you nothing if d of g is kind of smaller than log of g. Right, so here if you know that, say, your d of g is at least a big constant times log of g, then you know that this d of h is at least a big constant times log of h, and you get this big constant as a lower bound on the size of h. But also, unfortunately, something like this is necessary, because if you think about your graph as being a disjoint union of cliques, of its average degree, sort of, well, you'll not be able to find the big expander that lives there, right? The only thing we have here is the average degree of G that we're working with. So that's a valid G you start from. So you can't really generally hope, but there is various, we'll get to some things like decomposition lemmas, in which we will try to a bit later in the course, in which we'll try to still kind of tile the whole graph with this type of pieces. So get something that gets a bit closer to regularity lemma type statements, where we kind of partition the whole graph. But very good question, thank you. Any other questions? Very good. Okay, so that's the lemma. Let's prove it. So there's a reasonably nice proof, and I think I'm done with that. So take H, subgraph of G, and I think I want it to have at least 2 vertices, but that's not really that important, such that it maximizes a certain potential function, which in this case is just going to be d of h divided by log number of vertices of h. Okay. So the reason I put this here is all my logs are always base 2. If I didn't say it already, I meant it. So I need a 2 so that this doesn't go to infinity if you put a single one. And then occasionally we'll need to be a tiny bit careful about h being size 1. But we'll see that in a moment. Right? So this sort of makes sense. You want to pick the densest spot in your graph. Right? And you want to, because if you pick the densest spot, then that means that kind of whenever you look at a cut in that densest spot, well, you should not be able to kind of find, it should not be sparse, because that would mean that kind of either side of the cut should have too much density and it would be a better choice for you. And this is really the whole intuition behind the proof that's going to show up now. But this maximization is kind of helping you do it in one step. So actually, another way of proving the same lemma would be to just follow what I just said. So if your graph G is not already a robust sublinear expander in that sense, there is a set U which doesn't satisfy that. And then just use it to cut your graph into 2 pieces, and then zoom left or right and repeat. So what this does is it sort of just picks the local optimum of that process and goes there immediately. Makes for a much cleaner proof. But both work, and we'll see the other one for the decomposition. Very good. So now let's see first one property that this gives you is sort of immediate, and this is this one, right? So why? Because we can compare H to G, right? So we know that d of H divided by log is at least d of G, because G was a perfectly valid choice for our sublinear expander. And if you move that log H, you precisely get the degree guarantee. Okay? So this bit we're happy with. So the more tricky bit is to show that this H now actually has those expansion properties written there. So let M be the number of vertices in H. Let D be the average degree in H. So I'm just setting up a bit of notation. And suppose for a contradiction or towards a contradiction, that there exists U subset of vertices of G and F subset of edges of G, such that, let's say, U is equal to n to the 1 minus epsilon is equal to the size of U. Size of F is at most epsilon d over 4 times U. and the size of the neighborhood in G minus F. So I'm really just doing a contrapositive of what's written there. Of U is less than epsilon U over 4. Yes, thank you. And all G's should be H, indeed. Thank you. Thank you. As I said, typos, and this is a very bad one because we really now care only about H, and there is this nonsense G that we started from, which plays no role anymore, but yeah, please do point out if I forget that. Good, right? So the only thing I did there is it failed that definition for some U, okay? Now, let me define. So this definition now doesn't matter because it's written there. It can go away. And now let's look at two graphs, and let's invoke our maximization property for these two graphs. So the first one is going to just be, so let H1 be H induced on U together with its neighborhood in this H minus F. And so this is a definition. And let H2 just be its complement. Complement of U, not of this thing that we took there. So in terms of a picture, maybe I can fit a picture there. We had our H, we have our U, let's say U is there, and then we have this, we had this forbidden edges F. Let's do something there. This is F, and then we are left with this two small neighborhoods, G minus F of U. Yes, thank you. Let's count how many times I'll make that mistake. Very good. Right, so then what I did is I took this graph as H1, right? U together with this tiny neighborhood. So it's because this neighborhood is tiny, it's actually pretty close to size of U. And I took the complement of U, which is just this, as H2. Okay? And the rest of the proof is more or less just invoke this maximization property for these two graphs, and then compare their number of edges to the number of edges of the origin. So for that, the kind of key, or like easy observation, but the key relation between the number of edges is that the number of edges in H is at most the number of edges that live in H1 plus the number of edges that live in H2 plus the size of F. Right? So if you think about this picture, once you delete F, the only edges that can exist are either within this H1 graph or within the H2 graph, where we're counting some edges twice, the ones that live inside of this small blob here. But it's kind of tiny, so it doesn't really contribute much, and I don't think it actually, I'd never seen that being usefully used. So, but if you add those edges, you get equality here. Make sense? Good, so now let's just write this in terms of maybe the degree. So this is degree of H times M is smaller or equal than degree of H1 times M1, where I should have defined M1, d of H2 times M2. Plus twice F. And it's twice F because we multiplied by 2 to get these things, right? But not that it matters that much. So M1 here is the number of vertices of H1, which is at most 1 plus epsilon over 4 times U. And M2 is number of vertices in H2, which is just m minus u. Right? So we know that this set had size u, and it expanded by at most epsilon over 4 factors, so we get that upper bound on the number of vertices there, and this guy just is the complement of u, so it has that size, that number of vertices. Very good. So now we want to actually plug in the maximization property, comparing h1 to h, right? So that tells you that d of h times m is smaller or equal, well, I guess I could have just copied, but let me put both. So we get d of h. We get divided by log m and multiplied by m1 times log m1. If I did that correctly, right? So d of h1 divided by log of m1 is smaller or equal than d of h divided by log of m. That's just what picking this one as a maximal one tells us. And also the caveat about this being at least 2, it's actually also true if h1 is a single vertex. It just, this disappears because it's 0 and everything is fine. So it's also true not by maximization property technically when m1 is 1, but it's still true. Right, because otherwise if this were not true, we could have used h1, would have been a better choice than rh. And we get the same on the other one. And we have our bound on f, which was twice d of h times epsilon over 4, so this becomes a 2, times u. Right, so we assume that our number of forbidden edges isn't too large, and we just plugged in that inequality. And we plugged it in because we can now cancel stuff to make things nicer, so this goes away. Very satisfying. Right, and we can now also just multiple, so we want to get some better upper bounds on various things that are happening here, so we want to plug in what exactly m1 and m2 are and see what that tells us. So we are getting here that m is smaller or equal than, so m1 was at most 1 plus epsilon over 4 times u, right? So I plugged in what that is, times, so here we have this log m1, and it's again going to be a log of that, and a log of that is just a log of u plus the log of this, okay? And the log of u, because u is n to the 1 minus epsilon, is just, well, m to the 1 minus epsilon after the correction. So log of m to the 1 minus epsilon is 1 minus epsilon times log m. So what we are getting here is 1 minus epsilon times log m plus log of 1 plus epsilon over 4. And epsilon is small, so I mean, it's always true, but it's not a bad inequality. So that's just at most epsilon over 4. So I'm being a bit quick here, and this is the nastiest term to actually write out, but I'm just using basic inequalities that we get from the setup, okay? Just the fact that we know that this m1 isn't much bigger than the set u that we are expanding, okay? Good, and the next term is actually easier because this m2 we are just going to say this is at most log m and cancel it with the one at the bottom. So here we just get plus m minus u. Right? So m2 was m minus u, And we are kind of thinking of U also as being a relatively small set. I mean, it works for any U, but realistically interesting stuff happens there. So this is also not that bad of an inequality when we're doing it. And we get this U epsilon over 2. And now it's just clean that bit up. So we get M is at most 1 plus epsilon over 4 times U. And here, since M has size at least 2, we can put a log M here as well and then cancel the logs. So this becomes 1 minus 3 epsilon over 4. Right, I'm doing something very silly there, but this is a sort of irrelevant term. Right, and so still with this plus M minus U and plus U epsilon over 2. And maybe let me put strict inequality there because at some point I want a strict inequality. Well, I think I would have still been fine because the next one is. So what is, so this is times, not a minus. So if you multiply this and this is roughly 1 minus epsilon over 2. It's actually strictly upper bounded by that. And here we get epsilon over 2 times U. So actually this plus this is strictly less than U. So we get that this is strictly less than M. We get the contradiction. Okay? Again, this is something that is better done in the private of your own paper than in front of an audience. But I hope the kind of the actual idea of how you prove this lemmas is clear. And then once you actually do it, you can do it a bit cleaner, a bit messier. And this is the cleanest I know. But essentially, the same idea works for all of these pass-to-expander lemmas that I know of. Actually, I don't know that it's tight in any sensible. In some ways, yes, but in some ways, no. So there is actually a lot of interest if you figure out a genuinely different way of doing that, of finding this robust, or any expander subgraphs, I think. Yes, this is the one that gives already quite a lot of mileage. Very good. Any questions about this? Yes?
The other way that you mentioned,
Uh-huh.
you give an algorithmic version if you try the splitting one.
So the problem there is how do you find a subset which has a weak expansion, right? That's the part of this. So actually you are correct. You can make it into an algorithmic one by instead of finding the worst one, you find an approximately bad one. Gets a bit more messy. They actually have a much better hierarchy of this. There is very good efficient lemmas, even linear time lemmas that will decompose you into expanders. They will be a bit weaker than what we're doing here, but they usually don't so much care about the polylog factors happening. And for certain problems we do. But anyway, so if you care about fast algorithms of this, they have lots of tools to do that. And I think anyway, let me not go into that too much. But it's a very good question. And yeah.
So if you follow that algorithm, is there any reason it wouldn't give you just an in-use subgraph?
Sorry, say again, what?
Would H always be an in-use subgraph for G, or is it?
So for you, it's always beneficial. It's an increasing, this sublinear expansion property is an increasing property. So it helps you if you add more edges. So you just always want to take it. If it has more edges, it just expands better. So you can always take the induced if you wish. And technically, I could have said when you're choosing it, but a very good point. Any other questions, points, complaints? OK, good. So we have a pass-to-expander lemma. Great. So let's use it for something. Right. So where am I? I've done that. Yeah, I promised you homework. Yeah, so as I said, if you want to get a bit stronger pass-to-expander lemma, if you have a better degree guarantee, You can do that, just use the different function. Instead of this, use whatever is like, so let's say n to the alpha instead of log n here. If you have e to the root log n guarantee, use e to the root log n there. If you try to make a uniform lemma, I tried to over the last several weeks, you get a horror story coming out of it. So this is why you don't get one single unified lemma, but it's possible that it's doable, and I just didn't understand how. But let me give you as an exercise just to kind of highlight it. You get something actually nicer and better if you have polynomial degree. And right, so this is exercise, and I lost track of which number, but notes maybe did not. Show that there exists H subgraph of G such that H is an alpha over 1 plus alpha expander. And this, remember, was our just constant factor expansion, none of this robustness. You can add robustness, that's exercise 2, but this will make the proof a tiny bit cleaner. Although the only thing that it makes cleaner is that this term goes away, which didn't really cause a lot of mess in the whole proof there. With degree of H being at least degree of G times the number of vertices in H to the alpha divided by the number of vertices in G to the alpha. Right? So the key thing here is that this is a constant factor expander. It's not 1 over log n. So it's like our robust things, they become 1 over log n expanders when you try to expand big sets. Here actually get constant factor ones if you are denser than that. Very good. And the proof is more or less copy-paste what happened there, but it's not a bad exercise. Yes? You can choose it but as an absolute constant. If you start putting there 1 over log n, then you need to get a bit more careful, and you more or less recover what's happening. Yes, number of vertices of H divided by number of vertices of G. Yes, both are to the alpha. If you want, we can do. Very good. Right, so before we have log of H divided by log of G, and the proof is also just pick your potential function instead of log, have G of G to the alpha there. And again, if you think about it, this tells you nothing unless D of G is at least G to the alpha, because then a single vertex starts actually satisfying this, right? So you need something to push you up from being a silly, too small nonsense example. Make sense? And also you will get actually even stronger in a certain sense. You'll get much stronger expansion for smaller sets, and essentially everything that happens in the previous world happens here, except things become a bit messier and don't quite neatly tie into the log n world. And also you can do similar thing for constant degree ones. You just want to be much more careful about what function you will be optimizing, and you also want a cutoff at some point. You don't want to expand too small sets for that one. Because if you try to do this with a constant here, you will not get very far. So like it still needs to grow, it just needs to be kind of picked correctly so that certain integral converges. And anyway, I don't want to do the Komlós and Szemerédi ones. Very good. So they are actually super interesting. If you like, this is the one that had lots of applications, but I think it's not the best to see as the first one you see. Very good. So I promised some applications. So let's try to do one, or at least start, since I'm slow. Good. This is not the application. This is the application. Yeah.
So you said exercise 2 is just the same statement but with robust.
Yes, I think notes have a bit more stuff on it, but like exercise 2 shows small sets expand better. And it's really not a bad exercise because it teaches you how to kind of optimize these things if you want to actually do this. And exercise 3, show you get robustness as well. Very good. Okay, so the application I want to mention is something that was actually the origin of all of this. So it's a result which was independently proved by Bucić and Thomason and Komlós and Szemerédi in the 90s. And there is a funny story about it, that in about 3 weeks, there were 4 papers in the 90s which were improving the same result. So Noga was involved in one of them, and with Paul, and there were 2 papers of Komlós and Szemerédi, a weaker one and then a stronger one, and a little bit of the history of why these sublinear expanders actually took another maybe 10, 15, 20 years to actually start producing so many applications is because Bucić and Thomason proof is much nicer, if we are going to be honest. So everyone looked at that and missed that there is an amazing method in the Komlós-Szemerédi paper. And so this obviously over time got corrected. But this is, I think, a little bit what happened. It's a conjecture, not a fact. So I'd be curious to hear if people agree. But anyway, the problem is concerned with certain sensible objects. So a topological clique or topological minor of a clique, but I'll abbreviate, is a clique with some of its edges replaced by internally vertex disjoint paths. So AKA, it's a subdivision of a clique. So let me draw a picture. Here's our favorite clique. And what you're allowed to do is just put some extra vertices on every edge, which are unique for that edge. Right, so a clique is a topological clique, but also any graph that you can get from a clique by kind of subdividing edge, replacing edges with paths, is also a topological clique. So it's a bigger class of graphs. So a bit of the motivation for this is, so maybe let me just say AKA clique subdivision. So the kind of most basic extremal problem is how many edges do you need to have in a graph to find a clique, right? That's what Turan's theorem answers. And it's actually quite useful to find cliques in your graphs when you're working on a bunch of different problems. But unfortunately, Turan tells you you need to have a lot of edges in it. So how about trying something which has some properties similar to a clique, but is a bit weaker, looser, and try to find that. So this was a question that was asked independently by Erdős and Hajnal and Mader in the 60s, and then solved by Bucić and Thomason. So really the question, and that was, I'll not write the question, I'll just write the theorem, tells you that it's actually true that you get these at much lower densities. And so let me write what they proved. So this is Bucić and Thomason and Komlós and Szemerédi. Any graph with average degree D has a topological clique. So let me write has a k omega of root D subdivision. So the order of the topological clique is the number of so-called anchor points, so the ones that kind of play the role of your actual clique. And so if you think about it as subdivisions, then it's a subdivision. This is a subdivision of a K5. So I'm just saying that it has a topological clique of order at least constant root D. Okay? It's a very nice, clean theorem. And unfortunately, I don't know how to prove it without using this very sparse version of Komlós and Szemerédi there. I know how to clean up about 3/4 of their proof with various different things, but there is still some bits that don't know how to fully push. So I'll prove a much shorter and slightly weaker result that goes through with the stuff that I told you and kind of illustrates also quite a few pieces of the argument that actually gets you there. What I want to prove is slightly weaker, or this is true, or like G, any G, and vertex G with D of G is equal to D has a topological clique of order omega D over root D over log squared n. So I'll pay a polylog. And you can notice immediately why I'm kind of slightly cheating you in the sense of if D is a small polylog, then this is saying almost nothing. So that allows me to assume that D is at least polylog, and our machinery starts to kick in and work very nicely. But still, it illustrates, I think, several kind of standard ideas that people use with these things, and I have some running chance of doing it in 13 minutes. Yes, very good. So proof, so pass to robust sublinear expander H, subgraph of G, right? And also observe one thing that I forgot to say, which is actually quite easy from the definition, is that these robust sublinear expanders have a minimum degree condition as well. Right? So if you expand a single vertex set in the definition, then epsilon is just 1. So you get that the number of edges you can delete is epsilon times the average degree divided by 4. That becomes average degree over 4. So minimum degree is at least average degree over 4. If you look at the proof, you can get actually an average degree over 2 just by using the maximality definition we used there. Doesn't really matter for us. But I'm mentioning it because this pass to expander lemma is in a sense like a very wide strengthening of this silly lemma that any graph of average degree D has a subgraph with minimum degree D over 2. So you can actually get way more than just that. That's what's happening in the pass to expander. Anyway, so here we get to assume that that our average degree of H is at least, sorry, the minimum degree of H is at least average degree of H over 4. And by the pass to expander lemma, what we get on this one is that it's at least D, so that's the average degree of our big graph G, times log number of vertices of H divided by 4 times log n. And here I'll actually just forget about this because I'm being wasteful and I'm letting myself have some polylogs, so why not have another polylog? And also because it's actually sort of hard to exploit the size of H into this because unless you are very, very dense. So what we do get is that the minimum degree is at least D over 4 log n in this H, okay? Right, and what we're aiming for is something like that. Good? So now what's our strategy? It's reasonably simple, and it's also hopefully not too complicated to write down. So fix arbitrary, however many points we actually care, so root d over log squared n many points, and I'm going to decide that these are going to be my anchor points. Okay, so you can actually choose them completely arbitrarily once you are in the expander. And now what do we need to do? Well, we want to join these things with internally vertex disjoint paths. But what are these expanders really good at? Finding short paths between different points, right? The diameter bound style argument. So the first one you get for free. You just get some polylog length path here. Actually, it depends on, if you did the exercise, then it's log n log log n. If you didn't do the exercise, then it's log squared n from last time, right? That's the diameter guarantee that we get in a graph. Okay, so first one's easy. Then how about the next one? Well, we do have a short path between this, but why does that path doesn't do something like that? Right? But we have this robustness stuff, so we can delete all of these vertices that we used on the first path, and our thing still stays an expander. So this is the reason for various choices of the parameters, and we'll still get the same diameter bound and can build another one. So the actual computation that is important here is, suppose we took a maximal number of paths of length, let's say up to log squared n, so that we don't assume that you did the exercise. Right, so I don't know, they go there, there, they all have that length. So how many, so let's call this t. So how many paths do we have? Well, there's t choose 2 pairs. And how many vertices did we use across all of these paths at any point of this algorithm? Well, at most log squared n per pair. Right, so and this is less or equal than d over log squared n. Right, so t gets squared. We multiply by log squared n. We get that this is the max number of forbidden vertices we get at any point in this algorithm. And now, because our expansion kind of tolerates 1 over log n, so we have minimum degree d over log n. So instead of starting from a single vertex, we'll start from its neighborhood. And in the first step, how many new vertices we get if you just use the naive 1 over log n bound? Well, d over log squared n. Right? This is the number of new vertices you get in the stage. So this does not block you. Well, I want some constant somewhere, but maybe this is, what did I put there? So put here 100. Right? Very good. So we will not get blocked, and we will be able to do the diameter bound. So let me now maybe write things a little bit more precisely. Yeah?
How do you define vertices? Because of the robust sublinear expander definition?
Yes, so I am not using the, so here actually you can forget in some sense the robustness for this application.
Oh.
If you want to go back to the root D, you need to actually take it back and do something with something similar. But here I'm just using the basic robustness you get from the vertex expansion, that if I delete less than half of the number of new vertices you get, I don't kill your expansion. So let me write it up, but that's the proof, essentially. Right, so let V1 up to Vt be distinct vertices. So these are all choices for the anchor points. So in the picture, they were here. And consider a maximal collection of internally vertex disjoint paths of length most log squared n joining distinct vi vj I less than j. Right? So you fix your anchor points, you keep adding paths so long as you can. If you actually add the path between any two, you're done. That's your topological clique you want. So assume that there is one where we don't. If T choose two such paths, we are done. So assume there exists vi vj without a path. Very good. So the number of vertices already in the picture is at most t plus t choose 2 times log squared. Right, so that's the computation we did there. You have up to t, actually minus 1 you can get if you want because you're missing 1, but we are being wasteful anyway everywhere. So, and this is at most, what did I put there? D over 100 log squared n. Right? And now the final bit is we want to say that balls around vi in the graph with these vertices deleted still grow correctly. So let me write that. So let fv be this set of vertices. And let me write this correctly. I want a ball of radius L around vi with fv removed to be bigger or equal than 1 plus 1 over whatever we had 4 there, so maybe 8 log n to the L minus 1 times d over log n. And I forgot what we had for the minimum degree. We had the 4 there. Right, so for when L is 1, the expansion factor, this is just the neighborhood. Right? The neighborhood, okay, with most half of the vertices removed. So let me draw that picture. So here's a vertex. It has d over 4 log n neighbors at least. And our forbidden set of vertices is at most a tiny bit, so we just forbid it. We took it out as f of e. But now the key step is actually in the next one, when we try to expand this set. Right? So what we are guaranteed is no longer controlled by the degree. It's just 1 over log n expansion factor. Our expanders are sublinear expanders. This is even with 1 over log n is the only thing I'm using. So what you get that in the next one, this has size at least d over 4 log squared n. Well, I guess I lost another constant somewhere there, but right? But still, because we just got the log squared here, the forbidden vertices make at most half of it. right? And the third time you're expanding this whole thing. So it again has size at least d over 4 log n, so you will not get stuck. So the conclusion is written in that slightly unpleasant expansion condition. And it tells you that if you plug in your L to be log square, actually if you plug in L to be log squared, you will reach more than half of the vertices. You do the same for J, and you do the diameter argument, and you're done. Make sense? So the thing to take from this that is really kind of showing up and that really tells you kind of the best what you can do is to think about how much you can get blocked at which points in time. Okay? So, so now do diameter. Bound argument and done. But yeah, so of course you can do quite a bit better with the polylog factor. So here's your exercise. Improve polylog. Exercise 2. Prove full theorem in the dense case. So average degree at least epsilon n. And exercise 3, prove the full theorem of Komlós and Szemerédi. So this comes with a star. There are several clever ideas extra needed there. This is actually an ingredient for this. And they use regularity, but you can actually get it pretty cheaply from what I've showed you, except you want to use that slightly stronger version of expanders, which you get in the polynomial regime than the ones I told you. Because you need to lose nothing at any point in the process somehow. Very good. So let me stop here, and we continue with some other applications tomorrow.